All right, so DNS security. You need DNS or the internet becomes almost useless. Technically, some traffic can be carried without DNS as long as you know the numerical IP address of where you're going, but almost no system uses direct numerical addresses anymore. Everything uses alphabetic names like this, ccsf.edu. So the DNS itself can be attacked so it stops working. It can be used to assist other attacks, and you can use it defensively to detect attacks or other malicious activity. And then there's the security and privacy problems caused by DNS, which are pretty considerable. So DNS itself, one thing you can do is stop DNS from working, and that will basically freeze up the internet or some portion of it. In 2001, people managed to take down Microsoft's DNS servers, so that would cause you not to be able to reach any of Microsoft's internal web pages. And that turned out to be because they sent all their traffic through a single switch, and they were able to flood that switch with traffic. And this was not uncommon at that time. 25% of large companies did have a centralized DNS architecture, so because of this, they realized they had to move to a distributed architecture that avoids a single point of failure and has multiple devices with multiple routes to them. All right, there was a botnet in 2004 that defeated the distributed architecture and blacked out Google, Yahoo, and other websites as the attackers found ways to create such a large flood of traffic that they could overcome even a distributed site. And then in 2002, somebody tried to take down the DNS root servers, which we'll talk about. There are 13 root servers that are at the heart of DNS, and people have tried to take them down many times, and they've never managed to take them all down, ever. If they did, we'll talk about what effect it would have, and the answer is it wouldn't have much effect unless you could take it down for more than a day, and then it would start to cause parts of the internet to black out. But that has never happened. And so the point is the root DNS servers are very over-provisioned. It's not really 13 physical servers. It's 13 groups of servers, each of them with many copies geographically dispersed with Anycast, which causes all the traffic to them to get smeared out all around the world. So unless you can take down all of them, you don't take down the service, and people have never been able to do that. There was a 2007 attack, and they put a gigabit per second in, but only 2 of them were affected because they weren't yet using this Anycast technique. If you take your Cisco and you learn IP networking, there's 4 kinds of networking. There's unicast, point-to-point, broadcast, multicast, and Anycast. And Anycast is the one used for this, where you take the same IP address and attach it to many devices at different locations, and then the internet will automatically, when you try to go to that IP address, the border gateway protocol will automatically route you to the nearest one that's up. And if it goes down, it'll just automatically route you to the next one that's up across the whole world. So it makes you, all your servers act like they were the same and provide service as long as any one of them is up anywhere in the world. So this is a measure of the traffic showing a flood of traffic, but it didn't take down all the root servers. So DNS works like this. If you have a freshly booted up DNS server that does not know anything, doesn't have any cached information from previous requests, and then you try to go somewhere like ns3.ccsf.edu, it will look at that and they say, well, I don't know how to do any of this. The only thing I know is the root servers. That's built into the software of the DNS server itself. So it will go to the root and it will say, all right, is there something called edu? Can you find .edu? And it says, yes, edu is over here. Okay, it goes there, says, okay, is there something called ccsf.edu? And it says, yes, there is. They say, okay, is there something called ns3.ccsf.edu? Ask this one. So it has a series of queries digging through the tree to find this device if it exists, or to get a clear statement that it does not exist. And that's the process. After it's done that once, it caches that information, so it doesn't need to go back to the root again for a long time. Now it knows where edu is, so it doesn't need to ask again where edu is, not until that record expires, which is typically about a day. All right, so you can use plus trace to watch a dig, and let me give this a try with my terminal. I've got a Mac here, so it's Unix, which is good. All right, so if I do a dig, let's see if it's still ns3.ccsf.edu. It is. I got an answer. All right. So I got an IP address for that City College server. And if I do it with plus trace, let's see if it tells me more about it. Ah, yes, there we go. Now it shows me it does the whole process from the start. So here it goes to the root, which is called dot, and it gets the answer of the 13 addresses of the root servers, the ones I was describing that have never gone down. And then it gets a resource record signature, a cryptographic signature that could be used to verify the identity, the authenticity of this data. That's DNS Sec, which we'll talk about. Then it goes down here and looks for EDU. It finds EDU is serviced by these EDU servers. So it asks the root, where's EDU? And now it's in contact with EDU, so it asks EDU, where's CCSF? And it gets this information about CCSF. It has 4 name servers that will tell you more about CCSF servers. And then it asks one of them, where is this particular thing called NS3? And it gets an answer. So the plus trace goes through the whole series of steps. All right. All right, and that's what you see here. Now, if you are a client going to the web under normal circumstances, then you just query your local resolver, which is typically your router at home. You have a router, and it serves as a DNS proxy, essentially. It's a recursive resolver. So it doesn't know anything. It goes and finds the answer, but it does have a cache. So this client might go to like a CCSF website, and if this client goes to a CCSF website, it will ask the local resolver, and it will say, well, I already know where it is. I already have that number. I don't need to ask anybody else. It's in my cache. So the fact that there's caching at any levels here means that very rarely do you have to go all the way back to the root. Most of the time, most of the queries are in a memory of one of these machines at a lower level. So you can poison the cache. So if I could trick one of these intermediate servers into putting in a false record, then all the clients going to that server would get lies for some period of time until the false record expired and a query replaced it with a clean record. So this has happened many times. Many attacks have been able to poison a cache, and that means you can redirect traffic for perhaps a large group of companies. If you can hit a major cache, like for example a Comcast DNS cache, you might affect all the Comcast customers in a large region of the country. And there have been people that have various ways to do this. The most famous one was the one Dan Kaminsky found. A very famous, very beloved ethical hacker. He found a way to poison DNS cache records in 2008, and he managed to keep it secret, and he managed to get the attention of Microsoft and all the other important companies and get them to patch it before it was ever exploited by criminals. It was one of the few examples of such a serious vulnerability being well fixed before anybody got hurt. Another one was DNS Changer. There were several of these attacks. This malware changed computers' DNS entries. Every computer has DNS addresses attached to your network card. You probably get them from your router or your ISP, although you can set them manually. And this malware would change it to a malicious one under control of a crime group, so they would redirect your traffic to the wrong website, and then they can trick you into putting your banking login to a fake bank page and things like that. So that's the first part of this chapter 1. Now let's do a Kahoot. These Kahoots are just little quizzes I do in class. They're worth extra credit. You do not need to do them, but if you get in the top 3 performers, then you get 3 points of extra credit, and it adds up for some people. And it tends to stop people from falling asleep so much during the lectures. That's the main purpose of it. So go to kahoot.it and put in that address, that number, and a name. All right. Pog. I don't know what Kahoot Pog means. There are a lot of acronyms I don't know. All right, let's give it a shot. All right, so what would an end user notice if your local DNS resolver went down for an hour? The whole internet would be unavailable. If you had DNS, you pretty much couldn't get anything done. And if your local resolver went down, then you wouldn't have anything. Yeah, that's right. Collapse of civilization would be a bit of an overstatement of that situation, but you would not have the internet. There you go. All right. All right. So which attack did Dan Kaminsky create? All right. Yep, cache poisoning. That's the one. He was a wonderful, very smart guy. Died recently. You answer by going to kahoot.it and putting in that number. There's the URL you go to, and there's the PIN you put in. All right. All right, how many servers will be queried by this command? I see a flaw in that question. All right, the answer is 1. You can kind of tell the answer is not 3 because one of these should be 4 or something. But the point is it's going to be, it's 1 anyway. Normally you only have to ask one question, one server to get the answer because it's typically cached somewhere. 1 is the most common actual number in practice. That question is not perfect. That's part of why these things are extra credit. There are flaws with them. Anyway, all right. All right, so how many root DNS servers are there? All right. The reason it's 13, by the way, is because 13 is the number of server IP addresses you can fit in a traditional DNS response. All right. All right, how many servers will be queried by this command? Yeah, this time it's 4. We did it. The trace will now go through the whole thing from the root to the top level domain to the code, the company, and then to the specific server. So 4 steps typically. All right, so what will you notice if the root servers went down for an hour? Nothing, because most everywhere you wanted to go, that address would be cached somewhere below the root servers, and so you would load cache. The only thing that would happen is if there was a brand new website that nobody had gone to for more than a day, you wouldn't be able to find it. But most internet traffic would run through just fine. All right. So what port is used for DNS? Port 53, UDP for traditional DNS. Modern DNS often goes over TCP 53 as well. All right, and what protocol does DNS use? Okay, most of it's still using UDP, some of it's using TCP, and an increasing amount of it is using HTTPS with the new D over HTTPS protocol. Anyway, it's amazing how complicated DNS gets, but originally it was just UDP. And that's what most people are still using. All right. All right. All right. Serpent C will have to tell me who they are if they want to get their points, and so will this person. People who use fake names will have to come out of the closet if they want to get their points, but if they don't care about points, that's fine. Joseph B, however, I think that's a real name. All right. So, all right, I'm going to stop this recording.